The fifth technological revolution has quietly come upon us. Quantum-based technologies and pharmaceuticals are going to totally alter the world we inhabit. It's happening right now, as informed technology users already know. Artificial intelligence, quantum computing, portable laser technology, and various entanglement-based capabilities are just being introduced, gradually but steadily building upon the four great revolutions preceding it. Quantum mechanical technologies are, for the first time, based in a much more thorough understanding of the underlying physics that describes the universe. The first such revolution, the Industrial Revolution, was based primarily in the invention of steam engines by Newcomen and Watt, and the discovery and description of the laws of thermodynamics by Lord Kelvin, Clausius, and John Rankine. The second revolution was the Electrical Age, based in Faraday's discovery that electricity had two inherent components, electrical and magnetic. James Clerk Maxwell completed the laws, tying all of this together, and the electronic age was born, initially describing analog electronics for an entire century of constant innovation: radio, television, HVAC systems, electric motors, the electrical power grid, and mass production automation. The third revolution was, of course, digital technology, beginning perhaps in the late 1930s in the mind of scarcely remembered Dr. John Adanasoff and his assistant Barry. Recognizing telephone relays were essentially binary devices, ones and zeros, which thus required using base 2 arithmetic. Followed on by the legendary Alan Turing of Britain and John von Neumann in the USA during the Second World War, in which computer architecture was initially conceived. Immediately following that war, room-sized mainframe computers sprang up at universities, large corporations, and banks, until Ted Hoff at Intel brilliantly invented the microprocessor in 1968, the invention which finally opened wide the path for Bill Gates and Steve Jobs to alter the globe to the digital world in the 1980s. The fourth revolution was, of course, the splitting of the atom, consequences of neutron chain reactions and nuclear energy. This affected us at a very fundamental level. It altered the balance of power in the world, changed the calculus of war forever, and is today providing electricity in many parts of the world, along with powering mighty naval vessels from our stealthy submarines to the great aircraft carriers. Atom splitting led to the great particle accelerators, which have helped complete the standard model of particle physics. And so today's world consists of machines based in the laws of thermodynamics, such as cars and trucks and airplanes, Maxwell's laws underpinning analog electronics, like electrical generators and everything they run. And for the last 40 years or so, the digital age, based in von Neumann and Turing logical mathematics, has largely dominated the consumer marketplace, from the exponential growth of Amazon retail to the remarkably versatile smartphones residing in everyone's pocket. Nuclear energy, based primarily in Otto Hahn, Lisa Meitner, and Enrico Fermi's original research, plays a significant global energy role today, both positive and provocative. Thus, there were four primary revolutions of technological development since the time of Sir Isaac Newton: laws of thermodynamics, electromagnetics, logic technology, and the standard model of physics. The fifth revolution saw its beginnings in the Solvay Conference of 1927, when the greatest minds in theoretical physics came together and began to debate the consequences of Einstein's discovery of quantum mechanics. Then came Bohr and Schrödinger and Dirac. 91 years later, quantum mechanics is finally beginning to be realized for its contribution as the fifth great revolution of technology. It will turn out to eventually be the most significant of them all. As we know, quantum mechanics is the underlying reality of all that we encounter in the physical universe. We know now that quantum mechanics underlies and describes the operation of the original germanium transistor, the silicon semiconductor, the laser, and even experimental single-cell biology. But in order for quantum mechanics to fully mature into the fifth great technological revolution, it has to make a significant mark in everyday life. Quantum computing is just happening. IBM is just now producing a 50-qubit computer. Lasers have become a part of everyday life. But there's no quantum apps yet. Entanglement is fascinating, but multi-dimensional worlds and faster-than-light teleportation are still to be discovered and precisely quantified. Cutting-edge research into quantum biology is of specialized interest, particularly in Europe and Asia today. Quantum-based pharmaceuticals are definitely the future for finally conquering diseases such as cancer. Quantum jitters have recently been discovered in human DNA, perhaps leading to a formal description of mutations. But I believe that the big kickoff to the fifth industrial paradigm will become most evident within energy science. The fifth global technological revolution will be fundamentally defined, at least initially, through the discovery of the laws of the quantum mechanics of energy production and storage. The key concept in quantum mechanics, and the one we shall focus on in this lecture, is the fact that all electrons in an atom are discrete, and each identified by 4 quantum numbers, very much like a street address. The principal quantum number, the magnetic or azimuthal quantum number, the angular momentum quantum number, and the spin. No 2 electrons in any atom share all 4 of these characteristics. This is such an important concept, I cannot stress that more eloquently. Why is this description of electron discretion the key issue in quantum energy science? And that's simply because the electrons in discrete and different quantum states can perform different unrelated tasks. It's fundamental. For an example, we can look at a jar of jelly beans. In classical physics, all the jelly beans are considered to be identical. If it's a particular flavor you enjoy, fine. If it isn't, then the entire content is unpalatable to you. Now just imagine if all the jelly beans were discrete. Some are fruit flavored, others licorice, some root beer, others chocolate, some round, others spread out in a haze. You are perhaps beginning to get the idea. Electrons are very much the same way. They each have individual characteristics that make them precisely suitable for performing certain types of work. Now, some may move electrical energy in the form of electrical current. Some may move heat or thermal energy, curiously, by a completely different mechanism. Electrons exist in wave-particle duality. They can act as particles or waves, and they can become entangled, leading to some interesting observations that may someday postulate that the speed of quantum information transfer between entangled electrons is actually faster than the speed of light. Electrons can readily exist in superposition states. Electrons follow precisely probability distributions as they are elusive with respect to position and momentum measurements. Now, such avant-garde systems are currently being described. Shankar Ghosh first describes electrons in different quantum states in an insulating salt in his seminal 2003 Nature article. He demonstrated that some metallic salts display the quantum properties of energy level splitting and quantum entanglement when exposed to magnetic fields. Felix Binder's Oxford paper on quantacell design builds on Ghosh's work. Binder describes a much faster charging rate in quantum batteries when entanglement is present. Alecki and Fans in the 2011 paper discuss unity energy extraction. Hovhannissian continues that analysis in a 2013 paper and makes the claim that entanglement isn't even the most necessary characteristic, that multi-state, multi-partite operation can occur at unity with the only limiting factor the inputted Hamiltonian. All these papers lead to the conclusions that we have drawn in the first energy-based patents, the latest being US 9,222,371 on the last day of 2015, describing a unique mechanism for storing and releasing of energy quantum mechanically. This is truly revolutionary, a fundamental discovery in experimental physics. For decades, we have been told that energy storage is the key to sustainability for human civilization. It is one of the 2 grand challenges that 21st century science must make: achieving global sustainability going forward and understanding the root cause of DNA mutations initiating cancers. Quantum energy storage elegantly solves the first grand challenge of this century. Let's look closely at how a quantum heat engine might work, and if it reaches Carnot efficiency or potentially does even far better. Carnot has stood now for 200 years as the most efficient heat engine that can supposedly exist. But that means a purely classical thermodynamic engine, not necessarily a quantum engine, which extracts stored energy from electrons in 2 different quantum states and 2 largely independent systems. The only visible commonality between the two energy streams is the source of heat inputted to the system. If it were coal or oil, gasoline, alcohol, kerosene, wood, anything that burns, it would be classical. In a quantum engine, the heat inputted is not the result of burning. It is purely electric, microwave energy. Why would microwave energy make a difference between a quantum and a classical system, you ask? Microwave energy has the properties that enable the quantum engine to exist. It's not radioactive, as most molten salt, thorium working gas generators historically were. It is purely electric, dipolar in heating, and most importantly, microwaves are generated by the resonant cavity magnetron. Now, you may already have guessed that the purely electric nature of the thermalization process is the real key to the quantum engine, and you would be correct. And this is because there's two serial outputs of the electrons in two quantum states. One probability distribution of electrons involves itself in generating pure DC current. This is done by reacting with the cathode, cathodes being electron needy and thus attracting them. Electrical batteries facilitate electron transfer from electron-rich anode material to electron-needy cathode material in a loop, facilitated by an electrolyte, either liquid or solid. The electrolyte has a property known as enhanced ionic conductivity, and thus electrical current flows when the battery cell circuit is closed. These electrons exist above the Fermi band gap. They are called free electrons and can readily migrate through materials. In a quantum engine, this generated electrical current is only one output, the result of electrons in one single quantum state, or the free electrons. The other output is called heat transfer, and it is a totally different mechanism at the quantum electron level. Heat transfer is a combined function of four different quantities: electron, photon, phonon-lattice vibration, and a fluid particle. Researched extensively by Mahmoud Kaviani in his latest graduate level textbooks from University of Michigan. Heat transfer does not involve electron transfer ionically between anodes and cathodes, with free electrons above the Fermi band gap flowing from atom to atom as electron holes move in the opposite direction. In heat transfer, the atoms vibrate, linked together flexibly by valence-sharing electrons, moving thermal energy along like squeezing toothpaste from a tube. Thus, the quantum system uses electrons in two quantum states, immediately above and those below the Fermi band gap, in valence band and conduction band. So one operation is a thermal energy migration vibration, along with photon emission as excited energy levels degenerate towards the ground state, and the other is ionic leaping of free electrons in an ordered fashion, eventually winding up at the cathode. Since both of these operations occur simultaneously, and both occur as a result of the same initial thermalization event, they can thus be combined in various unique series or parallel products if the thermalization event is purely electric, as one output is indeed direct current. So now for the first time, we can take one output and bootstrap it backwards to the input of the other, placing them in series. It will be like a skyscraper with two factories on two levels, say the 37th and 45th floors. In a quantum system, the output of the 45th floor factory can be bootstrapped to the input of the 37th floor. This was how uranium isotopes were initially separated in two serial procedures. In the end, the product is some algebraic combination of the two. Now, if each factory were 70% efficient alone, then what is the total combined output? It is easy to say unity, but because of the addition of material science-based bond energies, particularly in the electrical generation axiom, it is conceivable that total system output can indeed exceed unity by emulation without voiding energy conservation, or at least drastically improve upon Carnot efficiency. This taking apart of energy quantum mechanically is fundamental. It is finally the energy breakthrough humanity has been waiting for since Volta created the first understood electrical battery. This is energy storage and release by pure mathematics. With only two variables to work from, combinations can be described, such as became evident early on in analog electronics, due to the dualistic nature of electromagnetic energy as described by Faraday and explained mathematically by Maxwell. Now, quantum mechanics has described thermal energy in two components, via electrons existing in two separate quantum states. Now the potential combinations can be as numerous and useful as those designed initially for analog electronic systems. The new second-order differential equation discharge is the result of 10 years of dedicated research into quantum-based energy storage and science. Overnight, it obsoletes all such classical systems like lithium-based batteries operating classically as single-axiom electrochemical reactions. This is as fundamental as Armstrong's accurate description of electrical amplification suddenly possible through De Forest's triode vacuum tube at the turn of the last century. Thermal energy can now be described quantum mechanically as a composite of electrons existing in multiple quantum states. This is the genesis of the fifth technological revolution, the realization of the quantum era. Following videos in this series will explore the mathematical foundation of quantum energy science as separate solutions of the Schrödinger equation and band gap theory. Like Maxwell's equations, it is the identification and separation of two intrinsic components that allows the vast toolbox of advantageous combinations to result. Classical energy science has only used one axiom of a dualistic structure due to mischaracterization of the quantum states of the electrons, and thus came to the wrong conclusions regarding maximum efficiency of energy generation and storage. Thank you.